Hello everyone, my name is Álvaro and I am a PhD student at the University of Colorado Boulder. With this paper, my colleagues and I want to introduce two potential magnetic enhancement technologies to boost the productivity of electrolytic cells in a lunar setting. As you know, in reduced gravity environments, the role of buoyancy is much weaker with respect to normal gravity conditions, which means that mass transport of gas bubbles in a multi-phase flow is severely limited due to this weaker buoyancy effect. The paramount example of this can be found in microgravity conditions, where the bubbles get stuck over the surface of the electrodes, as shown by Matsushima and co-workers in this paper. And this accumulation of bubbles leads to a reduction of the effective surface area of the electrodes, which means that our cells become almost ineffective. And for this reason, for instance, in the oxygen generation assembly, what we do is forcing the movement of water over the electrodes, so we flush this layer of bubbles. But of course, this countermeasure has also several drawbacks. Among them, the increased consumption of powers and the larger requirements in terms of mass, volume, complexity, etc. So in order to develop a passive mechanism to detach those bubbles in microgravity conditions, we came up very recently with two magnetic enhancement approaches. The first one is diamagnetic electrolysis. And in this case, what we do is polarizing the water by means of permanent magnets, that is, systems that do not consume any power, or passive systems. While in the second case, what we apply is the Lorentz-force effect. That is, in an alkaline electrolysis setting, we make use of this current flow between the two electrodes. We apply a permanent magnetic field, and then a perpendicular Lorentz buoyancy force appears that pushes the bubbles outwards due to the different phases and densities and the Lorentz force effect. However, these systems were initially planned for microgravity conditions. We were wondering if this would work also in lunar conditions. What we discovered by means of numerical simulation is, in the first case, in the diamagnetic case, is that if we have a 1 millimeter radius oxygen bubble in water, the lunar gravity acceleration will be the main effect in terms of buoyancy, which means that excluding very small regions in the proximity of a permanent magnet, which in this case is represented by this 1 centimeter radius, half a centimeter thickness magnet, only in those very small regions in the corners, we can observe a sufficiently strong diamagnetic force that actually attaches and deviates the bubbles from their upward track. In the rest of the domain, as you can see by the red arrows, the bubbles just go up as we will expect in the absence of the magnet, which means that diamagnetism does not determine mass transport in a lunar setting. However, as very recently shown by Farmani and Nasipuri, the presence of these small corner geometries, particularly in ferromagnetic electrodes, can induce significant buoyancy, micro-buoyancy effects, or significant enhancement in a localized region of the electrode. And this can effectively be used to enhance the productivity of our electrodes. But it does not have an effect in the overall mass transfer mechanism of the system, at least in a lunar setting. Regarding Lorentz force, as you probably know, the Lorentz force appears when you have a current and a perpendicular, well, it is, in the optimum case, it is perpendicular, but not necessarily. You have a current flow and a magnetic field applied, and then a Lorentz force applied perpendicular to those two vectors, G and B. The thing about this Lorentz force is that it is highly turbulent, and then it detaches the bubbles from the surface of the electrodes, leading to significant performance increases of up to a 14% increase in current density in the electrodes. In addition, in a lunar setting, this may be used to boost phase separation, which is very interesting, of course, because that will lead to reduce mass and power requirements for our system. However, to the best of our knowledge, nobody has ever studied this phenomenon in microgravity or lunar conditions. And this is exactly what we want to do in collaboration with Professor Brinkert and co-workers. The thing about this is that if we apply a Lorentz force perpendicular to the current flow of the electrodes, we will generate a significant mass transport effect. And this is what we want to test in microgravity conditions in parallel with this meeting, actually. Some preliminary experiments already show that the presence of the magnet induces a very strong buoyancy effect over the electrodes that is observed here in this video, for instance, in these small bubbles that are detached from the surface. So we think that the application of this magnetic force represents a huge opportunity to enhance the productivity of our systems in microgravity, yes, but also in a lunar setting. If you are curious about this phenomenon or have any questions, please don't hesitate to reach out, because we will be glad to have a conversation about this with you. Thank you very much for your attention.